Hello students, today we are going to consider discuss the excess pressure across the free surface of the liquid. Why we have to study this? Because we want to find out the excess pressure inside the liquid drop and inside the soap bubble. Now, once we understand this concept, that is excess pressure across the free surface of the liquid, we can also study the phenomenon of capillarity. Now, as you know, every molecule on the liquid surface experiences the force due to surface tension. The direction of the resultant force of surface tension acting on a molecule depends upon what? It depends upon shape of that liquid surface. That is, the liquid surface may be convex or concave. Now this force decides the pressure at a point just below the surface of the liquid. You will understand it clearly when we will actually discuss the liquid surfaces. Now let us consider plane liquid surface, convex liquid surface and concave liquid surface one by one. Now let Fa be the downward force due to atmospheric pressure. Now all the three diagrams drawn below show two molecules A and B. Point A is just above the liquid surface and point B is just below the liquid surface. Now the level difference between A and B is almost zero, and therefore this level difference will not contribute anything to the pressure difference, because we know that different points will have different pressures inside the liquid. But since we are considering the level difference between A and B as almost zero, it will not contribute to any pressure difference between A and B. Now pressure at point A is atmospheric pressure. Now in the adjacent diagram you can observe the plane liquid surface. When the free surface of the liquid is plane horizontal as shown in the diagram, the forces due to surface tension shown by Ft bar. Okay, the forces due to surface tension on the both sides of the imaginary line drawn on the surface act horizontally. Here you can observe that Ft, that is the forces due to surface tension acting on both the sides of the imaginary line drawn. Now these forces act horizontally. They are not having any component normal to the surface of the liquid. That is, they are not having any component in a perpendicular direction, and therefore there is no extra pressure on any side or on the either side of the liquid. Therefore the pressure on either side of the liquid, both the sides of the liquid is same. Therefore there is no extra pressure on one or the other side of the liquid. Let us consider now the convex liquid surface. In the adjacent diagram, the free surface of the liquid is convex upwards. The forces due to surface tension on both the sides of an imaginary line drawn to the surface have components directed in downward direction. Now in the present diagram, the Ft bar is not resolved. But if you imagine the resolution of the forces due to surface tension, then you can imagine that the horizontal components of Ft bar cancel each other because they are oppositely directed, and the vertical components get added, and therefore the resultant Ft bar is acting downwards. Now here Fa bar is the force due to atmospheric pressure. It also acts in the downward direction. So Fa bar and Ft bar. Fa bar is the force due to atmospheric pressure and Ft bar is force due to surface tension. Both act in the downward direction, and therefore the pressure at point B increases, which is inside the liquid, and it is on the concave side of the meniscus. Thus the pressure on the concave side, that is inside the liquid, is pressure on the convex side, that is outside the liquid. In short, the pressure at point B, which is on the concave side of the meniscus, is greater than pressure at point A, which is on the convex side. Now, let us consider the concave liquid surface. The free surface is concave upwards. Are you getting it? The free surface is concave upwards. Now here the forces due to surface tension on both the sides of an imaginary line drawn on the surface have components directed upwards. Here we haven't resolved the force again. If you resolve this force, then you will observe that the horizontal components get cancelled and the vertical components get added up, and these vertical components of the force of surface tension are acting in upward direction. But how is Fa bar? Fa bar is acting in downward direction, and therefore Ft bar and Fa bar are in opposite direction. Due to this, there is lesser pressure at point P. Now, as you can observe, the point P is on the convex side of the curve, and point A is on the concave side of the curve. Are you getting it? So here there is pressure difference between the 2 points A and B. At point A we are having higher pressure, and at point B we are having lower pressure. In short, you should remember that the pressure, the meniscus, the liquid surface can be convex, liquid surface can be concave, anything. But what you have to remember? You have to remember that pressure on the convex side of the curve is less than the pressure on the concave side. I will repeat again. What you should remember? You should remember this sentence. If you remember it, it will be easy to remember further derivations, expressions, and it will be very helpful for you to solve the numericals. Remember this sentence. I will repeat the sentence once again. The pressure on the convex side of the curve is always less than the pressure on the concave side. Now, we are in a position to obtain the derivation for the expression inside the liquid drop and the soap bubble. Hereafter, whenever we are considering the liquid drop or soap bubble, we are considering the small liquid drops and small soap bubbles, because whenever we are considering small liquid drops and small soap bubbles, we are neglecting the influence due to gravitational force and the effect of air resistance. If you consider bigger liquid drops or bigger soap bubbles, we have to consider these forces. But before considering the next discussion, we should understand why liquid drops and soap bubbles are spherical in shape. Why they are not in a shape like cube or say parallelepiped or any other geometrical shape. Yeah, here is the answer. Okay, the liquid air interface has energy. Now, if you are given a volume, then the surface with the minimum energy will be nothing but the surface with the smallest surface area, because we have considered the surface tension as the surface energy per unit surface area. Therefore, for a given fixed volume, the surface with minimum energy is nothing but the surface with smallest surface area. Now, if you compare the surface area of the sphere with known any other geometric shape, surface area of any other geometric shape, then you will find that sphere has the smallest surface area as compared to the uh, surface area of any geometric shape known. That is, maybe it may be surface area of the cube, it may be surface area of the parallelepiped, which is having same volume. And that is why the liquid drops and small bubbles are spherical in shape. Okay, now when these liquid drops and small bubble of spherical shape are formed, why they are not getting collapsed? They are not getting collapsed because there are forces acting on it. The external pressure and the force of surface tension is acting from outside to inside, and there is the pressure inside the soap bubble or inside the liquid drop due to the liquid inside, right? Now this pressure inside the liquid drop or inside the soap bubble is more than the resultant of the external pressure and the force due to surface tension, and this is the reason why the liquid drop or bubble is not getting collapsed once formed. Now, let us obtain the expression for excess pressure inside the liquid drop, which is also popularly known as Laplace law of spherical membrane. In adjacent diagram, you can observe the spherical drop having radius r. The pressure inside the spherical drop is represented as Pi and the outside pressure is represented as P0. Now as the drop is spherical in shape, the pressure inside the drop is greater than the pressure outside, that is Pi is greater than P0, and therefore excess pressure inside the drop, that is the extra pressure inside the drop, is represented as Pi minus P0. Now let us consider that the radius of the drop increases from r to r plus delta r, where delta r, that is change in the radius, is very small. Now since we are considering delta r to be very small, the pressure inside the drop remains almost constant. Now the initial surface area of the drop is represented as A1 and it is equal to 4 pi r square. Final surface area of the drop is represented as A2 and it is equal to 4 pi into bracket r plus delta r bracket square. Therefore, if you expand this bracket, it can be written as A2 is equal to 4 pi into the bracket r square plus 2r into delta r plus delta r square. Now as delta r is very small as compared to r, delta r square can be neglected. For example, if you consider r to r say 5 centimeter, Now what will, and if delta R is say 0.5 centimeter, then what will be delta R square? It will be 0.25, which is very small as compared to 5, right? Using this analogy, we will neglect delta R square as compared to R, and therefore A2 becomes simply 4 pi into R square plus 2R delta R. Therefore A2 will be 4 pi R square plus 8 pi R delta R. Therefore increase in the surface area of the drop will be A2 minus A1, that is 4 pi R square plus 8 pi R delta R minus 4 pi R square. Therefore increase in the surface area of the drop represented by dA is 8 pi R delta R. Now you have learned the surface tension in terms of the surface energy. You have learned that surface tension is nothing but surface energy per your unit area. Using that previous knowledge, we can say that the work done to increase the surface area dA is stored as excess surface energy, because the energy and work are interconvertible, right? Therefore we can write dW, that is work done, is equal to T into dA, that is T into 8 pi R delta R. This work is stored as excess surface energy. Let us represent this equation as equation number 1. Now this work done is also equal to the product of the force F, which is responsible for increase in surface area of the drop, and thus the displacement delta R, which increases the radius of the drop, and therefore we can write the work as dW is equal to F into delta R. Therefore F is what? F can be written as excess pressure into surface area. How much is the excess pressure? It is Pi minus P0. What is the surface area? 4 pi R square. Therefore force is what? Pi minus P0 into 4 pi R square. Therefore work is written as force into delta R, that is Pi minus P0 into 4 pi R square delta R. Let us call this equation as equation number 2. Now equation number 1 and equation number 2 both represent the work done, and therefore let us equate both the equations. Equating equation number 1 and equation number 2, we obtain T into 8 pi R delta R is equal to Pi minus P naught into 4 pi R square delta R. Delta R gets cancelled, 1 R gets cancelled, pi gets cancelled, and we are left with Pi minus P0 is equal to 2T upon R. Therefore we got the expression for the excess pressure across the liquid drop as Pi minus P naught is equal to Tt upon R. This equation represents the excess pressure inside the liquid drop. It is also popularly known as Laplace law for spherical membrane. Now let us derive an expression for the excess pressure inside a soap bubble. Now what is the difference between the liquid drop and a soap bubble? Now if you consider a liquid drop will have only one surface in contact with the air, whereas the soap bubble there are two surfaces in contact with the air, one inside and the another outside. Now, if all of you must have blown air bubbles in the childhood. Yeah, if you remember, if you recollect the formation of the air bubble, you will find that there is a soap film, and inside the soap film the air is trapped. Okay, and in this way the soap bubble is formed, and there, that is why the soap bubble is having two surfaces in contact with the air. One surface, outer surface, and one another surface is the inner surface. Now we'll consider the same procedure which was discussed for the liquid drop. The same thing, we will consider the soap bubble having the radius r, and then the radius r in increase from r to r plus delta r. Then we will find out the change in the surface areas, and then we'll find out the surface energy. Surface energy is nothing but the work done. The work done to increase the surface area is stored as the surface energy, and so on and so forth. Now the only difference is that whenever we are considering change in the area, the change in the area is two times, because there are two surfaces, and therefore the work done will be also uh, two times the work done in case of the liquid drop. We will not derive the expression again, because there are small changes. The changes are there in connection with the change in area, and hence the work done, and hence the excess surface energy stored. Therefore, this dW becomes T, dW is T into 2 times the change in the surface area, because there are two surfaces in contact with the air, and therefore this dW becomes T into 16 pi r delta r. Now equation 2 in the previous derivation can be carried over here as it is, because the equation 2 represents the work done uh, by the force to perform the displacement delta r. Now that force is excess pressure into surface area, and the displacement produced by the force is delta r. Therefore, this equation 2 remains same as in case of the derivation for the liquid drop. Here I am telling you that we are not repeating the derivation, because it is exact same except for this uh, term 2, because there are two surfaces, the inner surface and outer surface. We will derive in the similar way, only difference will be there in the change in the surface area, it will be twice. Therefore the equation 1 in this case will be twice that of the equation 1 in case of the liquid drop. The equation 2 will remain same as in case of the liquid drop, and if you equate these two equations as we have done in the case of the liquid drop, we will get Pi minus P0 the excess pressure inside the soap bubble as 4T upon R. Now it is exactly double the excess pressure inside the liquid drop, again due to what? Due to the two surfaces. The soap bubble is having two surfaces in contact with the air, and the liquid drop is having only one surface, and that is why the excess pressure inside a soap bubble is twice the excess pressure inside the liquid drop. What is the excess pressure inside the liquid drop? It is 2T upon R. What is the excess pressure inside a soap bubble? It is 4T upon R. This factor of 2 is due to the two surfaces in contact with the air, right? Now in the next slide I will explain this excess pressure inside the soap bubble in very simple manner without considering any kind of. Now here you can observe in the diagram, you can observe the soap bubble. There is air outside, it is soap film, and inside the soap film the air is trapped. In this way the soap bubble is formed. Now, if you travel from outside to inside, that is from convex side of the curve to concave side of the curve, the pressure increases, because we know that the pressure on the convex side is smaller than the pressure on the concave side. And by how much amount? It will be greater by 2T upon R, right? Therefore, when you travel from this direction to this direction, the pressure increases by the factor 2T upon R. Now, if you travel from this surface to the air inside, again you are traveling from convex side of the curve to concave side of the curve, and therefore there will be increase in the pressure. By how much amount? Again by 2T upon R. Therefore, whenever you are traveling from outside the soap bubble to inside the soap bubble, the pressure is increasing in all by 2T upon R plus 2T upon R equal to 4T upon R. This is the simple way to explain the excess pressure inside the soap bubble. So let us summarize what we have learned in this video. We have uh, found out the excess pressure across the convex liquid surface, concave liquid surface. We have therefore found out the expression for excess pressure inside the liquid drop and the expression for excess pressure inside the soap bubble. Now in the next video we will study very interesting application of the surface tension, that is capillarity or capillary action. Thank you.